just getting ready to start talking about how nobody was here. I was talking to a book bag, but never mind. Okay.
This is a very attentive book bag.
Yes. Noted more so than never.
All
right. Okay.
I can get something.
With caffeine?
Lots.
Yeah, okay. There is one new announcement. I won't go over the others, but this one, you may not be at all interested. I don't know if you are or not. Major workforce development announcement set for today on this campus.
Major workforce announcement?
Development announcement.
Okay. So this is an announcement.
Yeah.
So they're announcing a thing.
Yeah. Okay. And this was a press release. Alabama business, educational, and workforce training leaders will make a major announcement Tuesday, November 15th, related to the state's workforce development system. Our aim, this is a quote, our aim is to transform our workforce system into the gold standard for integrating the needs of employers and job seekers, growing the economy of our state, and raising the standard of living for Alabamians, announced Zeke Smith, Executive Vice President, Alabama Power Company, and Chairman of the Alabama Workforce Council. All media are welcome and encouraged to attend. Press conference participants and specifics are listed below, detailed below. What it is, a press briefing with Alabama business, education, and workforce training leaders to make major economic and workforce development announcements. When today, Tuesday, November the 15th at 2 o'clock this afternoon, Central Standard Time, where Lawson State Community College robotics lab in the Ethel Hall building that's right across the parking lot there. And it's, if you are thinking of going to it, you go to the lower level, the parking lot level, go in that way. That's the easiest way. You can go around the top side, but then you have to go downstairs to get to it. So if you go right into the parking lot level, you're there. Who? Zeke Smith, Alabama Power Company, Chairman of Alabama Workforce Council. George Clark, Manufacturer Alabama, Vice Chairman of the Alabama Workforce Council. Ed Castile, Deputy Secretary of Labor, Workforce Development Division. Fitzgerald Washington, Secretary, Alabama Department of Labor. And Jeff Lynn, Senior Executive Director, Workforce in the Alabama Community College System. Okay, so that's going on today at 2. If you're interested, I guess it's open to all. They sent it to us. I hope we're not expected to attend because I've got work to do. But workforce development, okay.
Sounds promising.
It does. It sounds good. Okay. That said, then, any questions on anything we've done so far? Okay. I think we're on page 151. We had just gone through these annihilators.
Oh, yeah, the annihilators. That's right.
Yes.
Okay.
If what?
If you wanted to go back or not.
Yeah.
Because it's been a little bit longer than, because we didn't do class on Monday.
Right. Yeah. Yeah. We had done 2 the previous week, I think, or sometime.
Thursday.
Yeah. And we didn't have class on Tuesday, but we did on Thursday, I think. Yeah.
Right.
Yeah. Tuesday I had a doctor's appointment. So basically, what we did so far in section 4.5, we have talked about some of these factors of linear differential operators, and that some of these annihilate other functions. Okay? Now, just a quick review of it. Remember what your D stands for. Oh, I'm sorry. Thank you.
So this is a very interesting PowerPoint going on right
now.
And you did start screencasting that, right?
Yeah, it's going. Okay. Waiting for that to come up. Remember what your D stands for. That's any differential operator, okay? Derivative. But when they do the powers, those are upper level operators, okay? So,
Not the lower levels. But
okay. Yeah, higher levels, okay? But it doesn't mean they're squared. That means those are way out. Okay. Higher derivatives, okay? So, summary. Differential operator, oops, let me get my pen back to black. Okay, D to the N. Okay, and remember that means nth order differentials. Okay, derivatives. Okay, that annihilates these functions. Okay, constants, and then all your powers of x. Okay, it doesn't annihilate x to the n, but everything up to x to the n minus 1. Okay, all those, the power functions. Okay, then we have another differential operator, d minus alpha raised to the nth. Okay, that stands for it annihilates each of these functions. E to the alpha x, x e to the alpha x squared e to the alpha x, dot, 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 up to and including x to the n minus 1, e to the alpha x. Okay. So that's what this differential operator annihilates. Okay? And then the final one, sort of a complicated looking one. D squared minus 2 alpha d plus alpha squared plus beta squared. Okay? And that's raised to the nth. Okay? And that annihilates all of these. E to the alpha x cosine beta x, x e to the alpha x cosine beta x, x squared e to the alpha x cosine beta x, dot, 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 up to and including to x to the n minus 1 e to the alpha x cosine beta x. Sorry about that. Okay. And not just those, but also e to the alpha x sine beta x, x e to the alpha x sine beta x, x squared e to the alpha x sine beta x, dot, 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 up to and including x to the n minus 1 e to the alpha x sine beta x. Okay. Okay. Yeah. So those are our three annihilators, and they'll get rid of any of those functions there. Okay. Now, where would those functions live? Those are your g of x's. Okay. So, remember, they say 1 here, but this is any constant. Any k, which is a constant. Okay. they say 1, but any multiple of 1, okay? And then any multiple of everything else there. So
the constants don't matter.
huh?
This, constants don't matter. Like it can be any constant.
Yeah, right, yeah. And I don't even know if it has to be real. I think we'll probably keep them real, but better. So what this gets down to then, when you have a L of y, which is that's some linear operator of your derivatives, okay, of y, okay. L stands for any combinations of the d's that you have there, okay. If that is equal to some function g of x, okay. Now, time out, let's go back. What we did in the previous sections was all deal with the homogeneous state. This is 0. What this section is doing is then saying, well, what if you had some g of x here? Now, no y's over here. The y's all have to be here. Okay? They should be derivatives of y and function y, anything to do with y, but they have to be in a linear arrangement. No y's in the denominators, no y's with fractional exponents. You know, they have to be linear. Okay? Powers of that. Okay? Then, if that is equal to some constant, not constant, some g of x here, where that g of x can be of any of these forms. And this is where it can be a constant, k. It can be any power function, x to m. Now, for some reason, they changed the m's now. They were calling them n's before, and now they're m's, okay? It can be any x sub m times e to the alpha x, okay? Sine or cosine, exactly. X to the m times e to the alpha x cosine beta x, and x to the m e to the alpha x sine beta x. Okay? Any functions of any of those forms and combinations of the forms, okay? Linear combinations of those forms, where m is any non-negative integer. M greater than or equal to 0. Okay. Non-negative integer. It could be 0 or not. Okay. But it can't be negative. Okay. And alpha and beta are real numbers. The alpha and beta reals. Okay. Then these three annihilators, any d raised to any power, d minus alpha raised to any power, and then this sort of odd one, d squared minus 2 alpha d plus alpha squared plus beta squared, that raised to any power, okay, will be your annihilators, okay. Now, so we now know that such a function g of x, if it's any of those kind of functions, can be annihilated, okay, by a differential operator L1. This L was your linear operator that made the homogeneous part. Now we have another L1, which would be from one of these, okay, but you want to do the L1 of lowest order. Okay. Now, for instance, pick any one of those functions for me, but you plug in some value for m. Okay, so any one of these here, any one of those things, plug in.
Might as well go with the most complicated, x to the, let's say, x squared e to the alpha x cosine beta x.
Okay. We're going to use this one with that being the 2.
Right.
Okay, so our operator we'll use would be this operator with n equal 3.
Okay, so
Because remember, that will only work for those up to n minus 1. So n would need to be 1 more than whatever your m was there.
Okay.
And then your alpha, whatever that alpha was, goes here and here. Whatever the beta was, goes there.
Okay, so if you chose x to the m e to the alpha x, you would use the d minus alpha to the n, right?
Right.
Okay. And if you just had x to the m, you'd use d to the n.
Right, exactly. And you always do an n 1 more than your m.
Yeah.
Right.
N equals n plus 1.
Right. That's the key. That's why they say L1 of lowest order. Okay. Now, and by the way, you can have more than one of them too. You know, the operator L1 of lowest order consisting of a product of the operators d to the n, d to alpha minus d minus alpha to the n, or d squared minus 2 alpha d plus alpha squared plus beta squared. Now you see, after a while they'll drop the parentheses here because they're just, the only reason they put them in here is to show that's your constant term. Okay? So it's okay to lose those. And
Because it's just adding.
what's that?
You're just adding.
Yeah, you're just adding, and then that actually makes this a parentheses here rather than a bracket if you wanted to do that, because they will show that later that way. Okay.
Every time you, not every time, but it's happened at least 3 times now. When you go to right on the screen, it blacks out.
Right. Yeah, I saw it blink. Yeah, I only saw it blink maybe one of those times, but yeah, I've done it before. And I don't know, it seems to do it worse on these made-up PowerPoint things. Yeah, I guess so. But when I'm writing on the others that are on the DVDs, they don't seem to do as bad. I don't know why, but we can live with it. Okay.
As long as it stays on.
Yeah. It's just not probably very good for the bulb to be going on and off like that. Okay. So then you apply the L1 to both sides of this equation. So it'd be a L1 here and an L1 there. Okay. Now, we know what L1 times that g of x in will be. If that's the L1 of lowest order that annihilates it, that makes that become 0. So now your new differential operator is L1 of L. Okay, that's what they're getting, and that's called the method of this. No.
Basically, what we're doing is we have an L of y, which is all the y's on that side.
Yeah, well, that's what your problem was.
Right, and then you have it equal to some g of x.
Right.
X's in it and so forth. Right. And what we're trying to do is get it kind of back to where we were, where all the y's are equal to 0.
Where all the
Y's are equal to 0.
Well, yeah, a new L that does that, and that's what you're doing. Yeah. So perhaps then it would be a good time to go on. Now they throw some other little things in here, and this is fine. By solving the homogeneous higher order equation, and of course this will be higher order because it's multiplying some things by it. Because this thing now equals 0, this equals 0. That's your thing. We can discover the form of a particular solution. Remember when we did the YP? Okay. I want to say the C stands for complementary. I think that did. When you they use these little weasels. We can discover this form, you know. They don't say how we discover it, but I think it becomes sort of intuitively obvious. It becomes sort of thing what that Y of P is. That's the particular solution. Yeah, exactly. basically, here's how I think of it. This may not be right thinking, but when you had this, the homogeneous form without the g of x in here, this gave you complementary solutions. Okay? Then when you do this times this to get g, then whatever, in addition to those complementary solutions, then the particular solution that's in addition to that, I think it kind of pulls out and says, oh, that's your particular solution. And then your overall solution, y, would be whatever the y sub c is plus that y sub p. Now remember, the y sub p is the complementary solution. That will usually have your constants in it. And you need as many constants as you have order of this equation here, the L part of the equation. And then the y sub p is the part that gets added to that, that basically is helping solve the g of x. Okay.
So y of c is, you have as many as the order of L of y, is that what you said?
Yeah, the number of constants you have in this one will be the order of that original
Shouldn't
setup.
that usually be 1?
Yeah, second.
Shouldn't that usually be 1?
Well, no, I mean, this could be d2 something plus d3d's, you know, something plus it, yeah, and then you'd have to have 2.
But the y's would have to be, okay, I see, I got you.
Yeah, that is some linear combination of your d's. Of course, they're not linear if they got cubes in them.
That's
It's a
what I
linear
was,
combination.
that's what
Yeah.
I was thinking, like,
Yeah,
it's not
that's why
linear.
they have the extra level of operations in there. The d's are your derivatives at higher orders, but the L is the linear combination of those d's that can be higher orders. Yeah. Let's see if an example will help. Not necessarily, but let's try it.
I think it might.
I think it might too. It couldn't get much worse, right?
I don't think we can make it any worse than
Okay. So here's your situation. Y double prime plus 3y prime plus 2y is equal to 4x squared. Okay? All right. Pretty straightforward, right? Then you do just the homogeneous part. Yeah. Y double prime plus 3y prime plus 2y is equal to 0. Do that part first. Okay? Now, you remember basically what we guessed to be a solution for this. Well, yeah, that is a trivial, the non-trivial ones. And that would be included in it. We would say let y equal e to the, I think they used m here, didn't they? Yeah. E to the m x.
So it's like e to the alpha.
Yeah, right. But they've been using alpha for something else. So, okay. That's for the particular part. Yeah. Okay. So we'll do that. Okay, then y prime is equal to m e to the mx. Perfect. And y double prime is equal to m squared e to the mx. And then with that being our guess, we'll plug that in and we'll have m squared e to the mx plus 3 m e to the mx plus 2 e to the mx equals 0. Well, guess what? We can factor out an e to the mx, leaving us m squared plus 3m plus 2 equals 0. And the deal is this thing can never equal 0. Ever. Ever.
Whatever you're multiplying by has to be 0.
So that's it. And this gives you, you could factor that to be m -2, yeah. Yeah. Okay. Which means y is equal to e to the minus 2x. That we'll call y1. That's a 2. I don't know why it came out so ugly. And y1, we could have reversed the order. y2 equal e to the minus x. Okay? So then your, yeah, you don't need to go back and do that. You can if you want to. But your yc, I think that stands for conditional. No, characteristic, yeah. Yeah, characteristic. Your characteristic solution for the homogeneous part would be C1, and see they call it a sub C, and then you use a C, C1 e to the minus 2x plus C2 e to the minus x. Okay. Now, if you had boundary conditions, initial conditions, something else, you could solve and figure out what those two numbers were. But in general, you don't. Okay. Exactly. And that's the next part. Yeah. Now, since this one, 4x squared, is annihilated by which of those? Which is in, what is in then? 3. D to the 3 would be your annihilator. Pick the lowest one, okay? Now, what you do with that then is that's going to multiply by your operator we had here, which was, and it feels like we're doing it all back again. That's multiplied by D2 plus 3D plus 2, and that's going to equal 0. Huh? No, it's not. It really isn't. Okay? Yeah. And then if you chose, okay, and at some point when you get used to this, that this is what that stood for, you don't really have to go through the e's again. You just see that the characteristic equation, is that it? Yeah. Yeah, okay, characteristic equation is merely the m's with those coefficients. You see? 1, 3, 2. Okay.
And you just pull out the e and the mv, which is equivalent to.
Yeah, and yeah, that's never going to be 0. So that gives you that. And you see, then, once you do this, that gives you the numbers there.
Well, let's see. The only thing you would have to be careful about, though, is your order of your differential, like your derivatives, gives you the power of it too, doesn't it?
Yeah, yeah.
Okay.
Yeah, you see that? Yeah.
I was like, it doesn't tell you what power it is, but then I saw the second derivative, the first derivative, and not a derivative.
Exactly. And in my mind, that's the only reason they introduced those operators in there, to ease you into counting those as exponents. They're not exponents there, but when you do that, then it makes them look like exponents, and then they turn out really being exponents here, and I don't know.
Just kind of,
yeah.
Like, just reach in your sleeve and pull out some flowers.
Yeah, okay. Okay. Now, you know what's going to work for that, okay? Then you just have to figure out what's going to work for your...
Would it be equal -2 and -1?
Yeah, yeah. And if you operated on these, this is the equation you get from that. And if you had used the same rationale and stuff we did before, then, with y equal e to the mx, then the only thing different here would have been, this would be an m cubed times m squared plus 3m plus, second,
That changes the game a little bit.
it does a little bit.
Because m and m squared can, well, if it's all the same m, then m cubed couldn't be 0, they'd all be 0, I guess.
Yeah, no, well, yeah. Okay, but you see, this factor is the same. This is m equal minus 2 and m equal minus 1. So you get those same ones before. What does that m cubed give you then? Okay.
So that would be -2 cubed, which is -8, and -1 cubed, which is -1. Right?
Okay, so that one more time.
You just cube what you got out of that.
Oh, okay.
So let's say m is -2, m cubed would be -8.
Right, okay,
And if it was -1, it'd be -1.
okay.
Making stuff up.
Well, no, okay. That would be true with that, but what they have here, these three m's, for that to be 0, and this looks so bizarre, that has roots of m1 equal, m2 equal m3, and they all three are equal to 0. And then the last two are the ones we had before. Thus, the general solution then would be okay. Remember,
We just don't have to even worry about m
okay, well,
cubed.
here's the deal on that, okay? That m can be any constant c.
That's what I was thinking.
Yeah,
That it could be anything.
Yeah.
Because if those give us 0 in the parentheses, then m can be anything.
Yeah. But you see, if indeed we started with this, okay, then, right, if that were a 0, then this would be some constant. Yeah.
It'd be 1 times coefficient.
Yeah, okay. The second one then would be, and remember how we did it before, that would be, okay, turn back to that the differential operator d sub n annihilates all these things. So in effect, those are the functions that we have here. The first is the constant, the next is a c1x, and the next is a plus c2 x squared. Okay? Then we have plus c3. Why they changed the number, I don't know. I would have done it the other way, but I'm trying to stay with the book. Then this would have been these, except it's now called, I'm sorry, this is 2, this is 3, and this is 4. Sorry. C4 e to the minus 2x plus C5 e to the minus x. Okay? That is your generic solution. Okay. Now, that's your general solution. Let me call it that. That's why. Okay? Well, we know that that looks just like our characteristics solution here. So that makes our particular solution C1 plus C2x plus C3x squared. Okay? Except they're no longer calling them that, and I don't know why they changed this again.
But it should be, it is the y of p, right?
Yeah, this is your YP,
Right.
okay, is equal to that. But now they don't call it that anymore. They say YP is equal to A plus BX plus CX squared. Okay, where for convenience we've replaced the C1, C2, and C3. It's really convenient, A, B, and C respectively. Okay, for that to be the particular solution, it is necessary to find specific coefficients for A, B, and C. Okay?
so convenient.
Yeah. So, yeah, here's what we do. That's our particular solution. So y particular solution prime would be what?
It would just be b plus cx, or 2cx.
2cx. Very good. And y particular solution double prime would be
2c.
2c. Okay, very good. Yes, or not 2c. Okay. Now,
Then the third one would be 0.
yeah, well, no, we don't need a third one because our original formula was this one. So the particular solution, y double prime, that would be, I hope I'm going to have room. Let me write it up here. Yeah, that would be 2c, that's your y particular double prime, plus
b 2c.
3 times,
3 times b plus
yeah, b plus 2cx
plus
plus 2
2 times
times
a plus bx plus cx.
a plus bx plus cx squared. That's got to equal 4x squared. Okay? Now,
I have no room.
I don't either, but I'm running out rapidly. Okay?
So we just gotta combine all this.
Now, let's do it as easily as we can. The You awake? Okay.
I saw it coming.
All right. Notice here, 2, the only x squared that we have here is 2 times c times x squared, right?
Right.
So that would be 2c has to equal 4, so that means c has to equal 2. Okay?
The thought process there is the only x squared component that we have is cx squared.
2cx.
Yeah, well,
Yeah.
it'll be 2cx once we
Right.
distribute that.
Okay.
How do you get that to equal 4x squared?
Yeah, c would have to be 2. All right, now, we can go to either one of the other two we want to. Got to do them all at some time. Maybe be easier to do the linear term next. That would be 6c. See, that's going to give you an x plus 2b. That's got to equal 0 because there is no x term over here.
You mean 3b?
No.
No, wait, where'd the 3 come from? Oh, there is
Yeah. 3 times 2c would be 6c
a
plus, and the only x term up here is 2b, or not. Okay. And then, but we already know that c is equal to 2, so this would be 12 plus 2b is equal to 0. That means 2b is equal to negative 12. B would be negative 6.
Okay.
Sorry, running short of space.
Where, alright, show me, alright,
Okay.
6c plus 2b, where did that come
Okay. 3 times 2cx.
from? Right.
That's the only term up to here that has an x in it.
Okay.
This is constant, that's constant. So this is 6cx. So I'm just going to leave out that. I'm just going to do the coefficients of x. 6c plus, and then here's a 2,
2b.
x. So 6c plus 2b. Those are all the ones, and there's no x term there, so those got to equal 0. Okay, but we already know that c is 2. So plug that in, and you get 2b is equal to negative 12. Divided by 2, b is equal to negative 6. Okay, it's sort of like back substitution in Gauss-Jordan elimination. Or Gauss elimination.
I was just getting confused
Yeah.
because I thought you were pulling it all out of the middle term, but you're actually pulling something from the middle term and something from the
Wherever I got the term with x in that power. Okay, Now the final one, and I guess we can go and erase some stuff here so I don't have to write so small anymore. Okay. I hope I don't need this anymore. I think I've already used that, so do that. Okay.
I just said I needed a new piece of paper.
Right. Okay. Now our constants. There's no constant term here, so all the constants have to add to be 0, too. That would be 2c plus 3b plus 2a equals 0.
Okay.
And we already know c is 2, so that's going to be 4 minus 18, because b is negative 6, plus 2a is equal to 0. I put a little a, I should have put a big one. So that'd be 2a is equal to 14. So a is equal to 7.
Okay. I'm trying to rewrite some of the stuff to where I can see what it says.
Yeah.
Because I was writing on top of stuff.
Yeah.
So 6c plus 2b equals 0. Plugged in for c, got 12c, 12. Yeah. 12 plus 2b
Equals 0.
and then b equals -6.
Right. Okay. So let's go back to our solution. Okay. And our overall solution, y is equal to, now, remember they put the a to be that first, so that'd be 7.
Can we, where's our overall solution?
What's that? Down here.
C1, C2.
Yeah.
Okay.
But then instead of C1, they made it A, C2 made it B, and C3 made it C. Why, I don't know. And then they had already changed to C4 and C5. They're going to go back and change those to C1 and C2 again, I hope. But
The C4 and C5, what did they change those to?
well, why they ever changed them is a mystery to me. Because look at step 3, they changed them back to C1 and C2 again. So why didn't they write characteristic solution first and then write the other and then have the C3, 4, and 5 being A, B, and C, and that would have made a lot more sense.
I'm just going to use D and E
Yeah,
and just...
yeah. So, no, but these are real, okay. This part, this isn't a variable anymore, okay? These are actual numbers.
Right.
So we have 7
Plus, or minus
minus 6x plus 2x squared. Yeah. Okay. And then you have plus C1 e to the minus 2x plus C2 e to the minus x. There is your solution. Okay. 2 constants that would be given from your initial conditions, boundary conditions, some sort of conditions that you would have to know about. And they actually just turn around and write this the other way. C1 plus C2 is in front, and then the last part there. It doesn't matter what order you do. But this is your particular solution.
Okay, so because looking for the particular solution, we need to kind of do the sort of like back substituting, find that first section, and then dy equals 7 minus 6x plus x, 2x squared. That would be our particular. And then our overall solution would be all the way through e to the negative x.
Do what? E to the
Negative
yeah,
x.
right. Okay. So, and they write the C1 and C2 first, and then the plus 7 minus 6x, okay, plus 2x squared. All right.
That wasn't too bad.
No, it really isn't. their method of doing it almost makes it more confusing than it needs to be. Okay, so
Just changing variables and kind of hopping around.
yeah, and it just not satisfying. Okay, let's see, and we may just do it. So let's do example 4. Okay, that was 3 we just did. My pen's getting so tangled I can't write with it. Okay, here we go. Y double prime plus 3y minus 3y prime is equal to 8 e to the 3x plus 4 sine x.
Okay, let me ask you something.
Yeah.
This is going to be, we're going to set it equal to 0, do that first.
Yeah.
But when we're doing the annihilator operator type thing, we have to do 2 of them?
Yeah. Okay. We have to do one for that, and then you do a linear combination of those.
Alright, okay. I'm pretty sure I was seeing where this was going.
Yeah,
So,
exactly.
I'm going to take the S here, it's going to be m squared minus 3m.
M squared minus 3m is equal to 0. What would that give us? Right? And m equal 3. Got it. Okay? So our characteristic solution, YC, is equal to C1 e to the 0, which is 1, plus C2 e to the 3x. Okay. Because remember how you start this thing, let y for that linear part e to the mx. Right. And probably a good idea to put that in there, but then do your the characteristic equation with just the m, the quadratic, solve that, and then plug back in. And the first one would be C1 e to the 0x, which would be C1, plus C2 e to the 3x. Done. Right. All right. So let's, for lack of anything else, let's call this YP1. All right. And that would be what kind of annihilator do we need for this?
Well, the first one is, okay, the first one we would need it was D minus alpha
To the what? To the n.
Which would be 4, or would it be 4x?
1.
It'd be 1.
Because you see,
Oh, x.
yeah, x to the, and this is x to the 0, so that would be,
X to the 1. Oh, wait.
okay. The x you see in there, which you don't see, is x to the 0.
There, okay.
Yeah, because it's 1.
I was looking at the wrong end.
Right, yeah. Okay, so that's your operator there.
I'm going to write it like that right quick.
Yeah. Okay. And what does that really stand for? That's YP1 is equal to Y prime minus alpha. Right? Oh, and by the way, I've been writing alpha. What is your alpha? I shouldn't have written that. I probably should have to begin with. But that alpha is the 3. The 3, yeah. Okay?
Why the three?
Huh?
Why the three?
That's
Oh, that's the place
Yeah.
before, 'cause it's
e to the alpha x. Yeah, right. Okay. Now, okay. I'm sorry. This was called the auxiliary equation. The answer is the characteristic. Okay. That's called the auxiliary equation. Get all these names crossed up.
I don't
Okay.
think you've used that.
Huh?
I don't think you've used auxiliary equation, but you had the characteristic equation.
Yeah, but this is the auxiliary. Yeah, we
You
used
weren't
it.
following anything.
Yeah, I know. Right. I think I called it the characteristic quadratic, but it's the auxiliary equation. Okay. Now, okay.
We need to do a YP2 as well, but
Yeah. Okay. So I think I probably ought to, just so it won't get confusing. Now that you see this, that's got to be a 3. Okay. They don't carry the alpha any further, so I wanted to go back and do it like they did. Okay. Now, in my mind, we could just deal with that, but they're doing them both at once. So let's go on and do this one, the YP2. Now, they're not using this notation, but to me, this keeps it easier to deal with.
the formula for that was
D squared. Yeah. Yeah, I thought it was a minus. I wanted to check that. It's minus 2. Now,
alpha.
yeah, but,
I'm going to go ahead and rewrite the
right.
equation.
But you see, the alpha here,
Isn't the same as the one before.
no, exactly. Because the alpha here would be, this, remember this one would be x to the m e to the alpha x, either sine or cosine. This is going to be sine of beta x.
So we actually don't have an alpha.
Or the alpha is 0, yeah. Alpha is 0. So we don't even need to put that one in. Okay? So the flip back, it's the equation 7 at the bottom of page, or near the bottom of page 150.
Okay.
The D2, yeah. Okay? Okay.
We would have a d squared. The whole second term wouldn't be there.
Second,
The whole second term would not be there because alpha is 0, right?
alpha 0
So the 2 alpha d
is 0.
So plus alpha squared gone.
0,
Plus beta squared,
which is
x squared.
what?
It's x.
No, it's the coefficient of x.
Oh,
1. Yeah. That's it exactly. Okay. Now that's not quite right. Okay. Those are the operators for it. But what they're doing is plugging in the function that we're using. Okay. And this is the part that's for this one, okay, they put in just the function part, not the coefficient part of it, just the function. e to the 3x here. And for this part, again, ignore coefficients and put in sine x, okay? That gives you the actual y, okay?
Here they go throwing stuff in there.
Yeah, but where they got it from was there. I mean,
Yeah.
this is the part that you got this from, so this is the function that goes after it. This is the part that you got this from.
But you leave off the coefficients.
Yeah, leave off the coefficient. We'll deal with that in a second. Okay. Okay. So those are going to be your two particular solutions. Okay? Okay.
I'll take your word.
Okay, sorry. All right.
We'll find, we'll see how it works
Okay.
out.
And again, that step itself, I don't really,
It's not that.
I don't think is even critical to it. And they set this equal to 0 and this equal to 0. Because what they're saying is when you multiply the annihilator by what you got, it's going to go to 0. That's where that came from.
Okay.
You could have the 8 in there if you wanted to, but it's going to 0. And the annihilator here, and that's what it is multiplied by that thing, and that's just a 4. So who cares? You know, it's going to 0. So I don't really care for that step in there. I don't think it's absolutely necessary to be there because we're not really going to use it that much. Okay? But if we took this back, now this is now a homogeneous differential thing. So basically what that says, and I just wrote that one down, what this is saying is if you work that out, this will be that first equation there. That would be, I'm sorry, the annihilator that annihilates that, and okay. And it's of as low a degree as you can get, okay? That annihilator would be and again, to me, why I haven't seen the purpose of writing that equation yet. Maybe there is one, but I don't see it. The annihilator that will take care of this for you is, and you go back and look, the least common one, the annihilator that will do that for you is x e to the 3x. The annihilator that wipes that out and makes that a 0 is going to be that one. Remember, the n is 1 greater than the m. The m here is x to the 0, so it's one more than that. Okay? And the one that does that for you, now this is the one that is a little tricky because you have to include the one that does this one will be x, okay, okay, no, since your n is, goodness gracious, your n, or in our case the m is 0, so the n is going to be 1. No, I'm sorry. Yeah, n would be 1. So it looks like to me,
They got a different
Auxiliary equation? No. Isn't it? This is the auxiliary equation. Isn't that the same thing they got? M squared minus 3m, and that's m times m minus 3. So yc is c1 plus c2 e to the 3x. Okay, yeah, okay. So that in blue, that's that part. Forgetting about that. What I'm not seeing now, I can see where they put in a new variable here, parameter, and they called it C3. And for the life of me, why don't you just go on and call it A? Okay? Why mess with the C3 and then change the C3 to A? I don't know. But what I'm having trouble seeing is for this differential operator, if you go back to page 150, your annihilator is your D2 plus 1. Okay? And that's what we got. Okay? The D2 plus 1 raised to the first power, the n is 1. So, oh, that's right. So n minus 1 would be 1. So you don't have an x term. Okay, I was thinking you still would have an x term, but you don't. Okay. Because the n is 1, n minus 1 would be 0. So you, x to the 0 is just a constant. Okay, so that's right. But you then you have e to the 0x, so that's 1. And then you have, but you have to put, and here's the part that is not intuitively obvious, you have to put, though I think we'll see we don't have to, cosine, yeah, I think you do, beta, and what's our beta? 1. So cosine x plus sine x. You have to include both of those. You can't say just because that's a sine x, it's going to be a sine x. And why is that? Because we're going to take derivatives of it. Okay. Now this one happens to work out, I think we'll see that, and we'll call this b sine cosine x plus c sine x. They put C2, 4, C5, or whatever. Why? Then the next step, they change them to B's. Why take the extra step? Just call them A, B, and C. Okay. So this is now your particular solution. Okay. Is this combination. Y sub P is this. Okay. This is the annihilator for that. That's the annihilator for that part. Okay. And what we do next. So, okay, you got it?
I'm just trying to see how we went from d minus 3 times e to the 3x to...
That's what I said, that part. I see no reason for that step to be in here at all.
That's not even relevant.
I don't think so.
So then we got, so you went from e, or 8e to the 3x to xe to the 3x, right?
Okay. Yes. This goes to this.
Okay.
Because your n here is,
Or your x to the
m
0.
here is 0,
Yeah, and you
so
do
the
plus 1.
n has to be 1.
And you forget about the coefficient. Coefficients don't matter.
Yeah, we're going to get to those in a minute. Okay?
And
And then here, I wish I had the big thing up here. It was d squared with a 2 alpha d, but the alpha is 0 because you have no e term here.
right.
Okay, so that's out of there. And then your beta was 1, so it's 1 squared. So that's where you got that. I just wrote it there just to show that's what you wound
How
up
did you
with.
get from 4 sine x to b cosine x plus c sine x? That's
Yeah, and the reason, and then what you do from here is, this is your coefficient. They were calling C3 or
Yeah,
whatever.
B.
So why not just name it B now?
B's
Get
fine.
it. And it had an x to the m, but m was 0 because this didn't have an x
So
in
the
it.
plus 1, which is x,
Yeah.
would be x to the 1.
No, it's, if you go back here, the x to the n minus 1. Okay. Okay. And this had a m of 0, x to the 0th power. So that meant m was 1, but then you go to n minus 1, which is back to 0 again. That's what I had to check before. I said, why isn't there an x there? Okay. And then you had e to the alpha x, where the alpha was 0, so that's out of there. That's a 1, 2. And then finally you have cosine beta x, but you also have the sine beta x. Now I think, just hang with those for now, because if this had a d in it, which originally it would have, then you need both of those. But since it's d squared, I think you'll see we don't need them both, but you need to put them both in there. Okay? It's sort of like, trust me. Okay? Believe me. Okay, never mind. If you had more derivatives in here, because when you take derivative, if you took an odd derivative of this, you're going to wind up with a sine. An odd derivative of that with a cosine. So you might need.
You got to account for both.
You have to account for both. If later you don't need them, lose them. Yeah, right. Okay, this is enough to drive it out of you. Okay. I'll keep talking, but yeah. Okay. All right, so this is our particular solution, and what we do with this is take the first derivative of it. Y particular prime would then be, oh boy, a good old chain rule. A e to the 3x plus a x e to the 3x. Okay? Minus b sine x plus c cosine x. Y particular double prime, wish I'd have put the ax first. I think I'll go back and do that. That would be an ax e to the 3x plus a e to the 3x plus another a e to the 3x. So that's going to be 2a e to the 3x. Okay. Minus b cosine x minus c sine x. All right. It needs to solve, you need to plug it in that order, so that's going to be ax e to the 3x plus 2a e to the 3x minus b cosine x minus c sine x. That's the y double prime, y particular double prime, minus 3 times y prime. This does have a prime in it, unless I copied it wrong. This is why we won't lose the sine or cosine. We need them both. Okay? So that's going to be 3 times y prime, which was this one. That would be 3a x e to the 3x minus 3a e to the 3x. I changed the order of those. Okay. Plus 3b sine x plus, oops, minus. Okay, I almost blew that one. I got on the wrong line because they all look so similar to each other. Minus 3c cosine x. Okay? And that's supposed to equal 8e to the 3x plus 4 sine x. Okay, now we start playing with our coefficients. Okay? I'm trying to see which one I want to start with now. let's just hit them right off the top, okay? The terms with x e to the sine x in them here have coefficients a minus 3a. That's it. So that's minus 2a is equal to 0, so the a is equal to 0. Oh boy. Can that be true? No. Oh man, sorry about this. Why particular, I forgot my 3 in here. Sorry. This had a 3 with it here. So this would have had, I'm sorry, I need to start over. You didn't miss anything, I took a derivative badly. Derivative badly. I was skipping steps or rearranging steps at the same time I was doing it, and I left off a number when I did that. All right, let's start over again. So glad you missed all that. Okay.
Probably good.
That's what I said. Glad you did. Y sub p is ax to the e to the 3x plus b cosine x plus c sine x. Okay, we got that. Now we take the first derivative of that, okay? So y prime, because we need it up there, is equal to, chain rule is first a e to the 3x. Okay, right, okay. Depends on which one you do first.
Oh, it's a product.
Product rule, right. So I did the x first, derivative of x, which is 1. So that's just a e to the 3x. And then when you do the second part, you get 3a x e to the 3x. Right. Minus b sine x plus c cosine x. Okay. And I forgot my 3 in there. Y particular double prime, because we need that up there too, is, this first part is pretty straightforward. That would be 3a e to the 3x, right? Plus 3 times a, yeah, another product rule, e to the 3x, right? Right. Plus 9ax e to the 3x. Okay, say that again. Yes, minus b cosine x minus c sine x. Perfect. Okay. Now, can we combine any like terms? Yeah. These two add to be 6, right? All right, and that's all we can do. The 3a to the 3x plus 3a to the 3x. Second?
And x coming down from the exponent that confused me.
Yeah, that was, when you take the derivative of that, you get 3a to the 3x. And when you take the derivative of this part, you get 3a e to the 3x. And when you take the derivative of this part, you get 9ax e to the 3x. Okay. All right. Now, so I combine those two. So now we write down that original equation, but using the particular solution derivatives, and that gives you 6a e to the 3x plus 9ax e to the 3x minus b cosine x minus c sine x. That was y double prime. Minus 3 times y prime. So multiply everything here by 3. That's going to be minus 3a e to the 3x minus 9ax e to the 3x minus 3b sine x.
You multiplied everything by what?
3. 3 times y prime.
Okay.
So it's 3 times,
The
yeah,
y prime. Okay.
yeah, right.
I got you.
Plus 3c cosine x. Right? Now we're beginning to forget that capital C. It looks too much like little c in cosine, so remember, okay.
Looks like you're trying to.
And this is supposed to equal 8e to the 3x plus 4 sine x, right? Because we did the y particular, double prime, single prime, 3 times, that's supposed to equal that. That was our original equation of it.
So what we want to do now is group the sine functions together and see if we can't set those equal to 4 sine x.
Okay, you certainly could start that way if you wanted to. So minus c minus 3b is equal to 4. Is that what you wanted?
Yes.
Okay. And minus b plus 3c is equal to 0. Right? Now, I probably should have written one of those in a different order.
Yeah, just switch the bottom around.
Bottom, okay. Put the plus 3c here and the minus b there. Oops.
This is the
Okay.
old elimination.
Okay. Plus 3c minus b. Is that right? Yeah. Okay. Multiply the top of them by 3. That would be a 9, and that would be a 12. So you have minus 10b is equal to 12. B is equal to minus 6/5. That's totally strange, but that is indeed true. B is equal to minus, well, okay, wait a minute. No, they got a plus, I think.
Hold on.
Let me make sure that I did my original the same that they did. Yeah, I did. Well, I think what they do, they're one that with everything, the negative of what we do. I think we're going to find that. And it doesn't matter. Plus, I mean, it just, the way we solved ours, they solved theirs a little differently. Okay?
Probably get all negative answers.
Yeah. Actually, where I was wanting to start is, but it's fine to do it that way. But if we had started with the A's, huh?
You can do the A's.
Yeah. Let's see. Okay, number 1. Here's a plus 9ax e to the minus 3, and there's a minus 9ax. So those terms cancel each other out. Okay?
It's funny because they were.
Yeah. And this is a 6a minus 3a, and that's got to equal 8, right? 6a minus 3a, that would be a 3a is equal to 8, right? The ones with the e.
Oh, it has an E.
3x.
I was thinking we're crossing that one.
Yeah. So a is equal to 8/3. It didn't matter. Okay, I don't think.
And that's because the 8e to the x, 8 3 to the x.
What's that?
The 8 came from the 8e to the 3x.
Right, yeah. That 8 came from there, and the sum of these two is 3a. Yeah. Now, why have we got an opposite sign for b? It may be just how we solved it, but it doesn't seem like it.
Right, so we went back through and multiplied by negative.
Okay, they have minus b plus, minus, wait a minute. Looks like I did copy something wrong. 3b,
I'll tell you what I think happened. All right, so you see your second, all right, so when we were doing this,
we said minus c,
this right here.
yeah,
Okay, so we were taking y prime. Where's y prime again? Right there. Okay, so y prime is that, but we multiplied this by -3, so this should be an opposite. This should be a positive
sign.
this should be a
That's it. Yeah, that's the plus and that's the minus. That's it. Okay,
And
so
right here,
then
third
that
line,
changed
positive.
that around and made that plus. Okay, so b is equal to 5, 6.
We found the error.
Got it.
We found
And
the error.
then let's see if we can get the c right then. Well, let's just go back and plug in. If let's see if I can write that first equation again. Minus c plus 3b is equal to 4. That was it, wasn't it?
Minus c, which would be minus b there. Or no, minus c is sine.
Yeah.
Plus 3b, yeah.
Okay. And if we just said that b is 6/5, that then would be minus c plus 18/5 is equal to 20/5, which is 4. So that would mean minus c is equal to 2/5, so c is equal to minus 2/5. And is that what they got?
Yeah.
Good deal for them. Okay. So we can write down our solution. Y is equal to the characteristic solution. I go blank on that word every time. And that was our C1 plus C2e to the 3x. Yeah, and a is 8/3, so it's plus 8/3 x e to the 3x plus b plus 6/5. No, that was cosine. It's cosine. Cosine x. And then minus, I think it was, if I can find it, yeah, there is minus 2/5 sine x. Okay, there's our solution. C1 plus C2 e to the 3x plus 8/3 x e to the 3x plus 6/5 cosine x minus 2/5 sine x.
So, when we were trying to find our A, B, and C,
Yeah.
we were matching it up with these coefficients. So for our A, we combined that one and that one, and they were both e to the 3x function, so we could compare it to that coefficient.
Okay, now these two went out, so there is none.
I'm talking about this one and that one.
That's one of those, yeah. And those added to up there, that wherever it is. Yeah. There it is. 6/5 6a minus 3a is 3a e to the 3x is
Which
equal to 8 e to the 3x.
So
So
30
that means,
divided by 8.
yeah.
Okay, got that. B. We had a B cosine and a B sine. Equals another sine.
No, you did the sine coefficients. Minus c
Okay, minus
plus 3b
plus 3B.
is equal to 4. Minus c plus 3b is equal to 4.
We just did the sines. Okay.
Right, and then we also did for cosine, minus b minus 3c is equal to sine, and that was this one.
Equal to 4 again?
Equal to 0, not.
Oh, equal, because there wasn't a cosine.
There wasn't a cosine.
Right, okay.
So that was
Alright.
equal to
See, I
0.
think the cosine was what was throwing me off. I was like, alright, we have a sine on this side, we have e to the 3x, but what about the cosine? But I didn't realize we said it equal to 0.
Right. You said equal to 0.
Maximum understanding has been reached.
Good. All right.
Just had to go over that last part. It was getting kind of crazy.
Right. All right. How are we doing on time?
I have no idea. 10:57. So we got.
We went to 10:45, didn't
Oh
we?
yeah.
Okay, so we went a little over,
Oh yeah.
but no
It was
extra
all
charge.
good fun.
Yes.
I
Okay.
got my tuition
So
support.
we got no extra charge though. Okay. We will begin next time with example 5. And I can't get my
I think we
pencil
covered
right.
some good ground.
Yes, we did.
Examples done. Started really getting
Oh, I see what.
annihilator stuff.
All right.
Yeah, and I know why it felt like I haven't been here in a while, because the last differential equations class I missed.
You did. Oh, okay. That one's on.
Where you talk to yourself.
Okay, so we'll do example 5. Let's do some homework exercises first. Any of the odds 1 through 9. Any either 11 or 13 or both. That's up to you. Any of the odds 15 to 25. I think we'll stop there, and because we're going to do a couple of, well, if you want to proceed, I think you can do any of the odds 27 to 33. Okay.
I'll start by working on my test.
And any of the odds 35 through 63. And then we'll hold off and do the initial value problems. So I don't see any in the samples. But we'll do those at the end then. Okay, good deal. And we finished 4-5. We'll almost finish 4-5. Right, we'll go from there. All right, we'll end this.